Hello guys, welcome to my channel. This is Ehsan, and in today's video we're going to look at another electronic quiz. This is our circuit. All the transistors are in saturation and the IB is ideal. Here with all these assumptions, we're going to look for the value, for the approximate value for Vout divided by I in. So if you're new here, please give me a thumbs up, hit that subscribe button and also the notification bell, so whenever I upload a new video, you'll be aware of it. Let's jump into it. Here is our problem. And here are all the possible answers for this problem: A, B, C, and D. The unit is in ohm because this is voltage divided by current. So in order to start this problem, it is better to start with the DC bias point. In the DC, the capacitors, these capacitors are open circuit. This capacitor again is open circuit in the DC. And this IAB goes through M1 and M2. So the drain current for M1 and M2 are this IB. So in the DC, IB is equal to I drain 1, which is equal to I drain 2. So I can calculate GM1, which is equal to GM2 for my AC problem, because in AC we had to model transistor with GM. We need GM. One of the formulas for GM, which had 3 formulas, which one is the best suitable for this question? So 2I drain divided by VGS minus V threshold. This is the best formula in here because we have I drain, which is 1 milliamp. We have VGS minus V threshold, so we can use this formula. So 2 times 1 milliamp divided by 0.2 volt, which is equal to 10 milliamp divided by volt. This is the answer for GM. Now, if we want to model transistor for our AC problem, here it's our transistor, our NMOS transistor, and here this is the VGS. And this is the drain current, which is GM VGS. That's the only thing that you're going to use for modeling these transistors in this problem, because we don't have channel length modulation, so there is no resistor between drain and source of this transistor. Okay, so this is the only things that you use in this problem. Now I'm gonna redraw the AC circuit for this problem to make it clear for you guys. Okay, here for AC, these capacitors are short circuit. So let me just, as a summary, in DC, the capacitor model with open circuit, and in AC, capacitor model with short circuit, because the impedance of capacitor 1 divided by C omega J. So in DC equals to F equals to 0. Because F0, omega is 0, 1 divided by 0 is infinity in DC problem. But in terms of AC, 1 divided by C omega J, because F goes to infinity, so 1 divided by infinity is equal to 0. So the impedance is 0, meaning that capacitor had to be short circuit. This is the difference between DC and AC when you model a capacitor. So here we have IA in. IA in is AC, so we have it in here. This capacitor is short circuit. Here we have M2, our transistor. Here we have R2 and R1, just the same, no change. Here we have the source of M1, which is the same in this model. How about VB? VB is the bias voltage, so you have to be connected to the ground. The DC voltages is short circuit to the ground in AC problem. And here we have this capacitor, which is short circuit, as we already discussed in AC. And here we have Vout. How about IAB? IAB is completely eliminated, which means open circuit in the AC problem. In the AC, you don't need your DC sources. So there is nothing in here. Okay? And this is M1 and this is M2. And this one was 100 kilo and this is 100 kilo. So now you're going to apply this model to calculate V out divided by I in this problem. You're going to need gate source voltages. Okay, so we had to define new voltages if you don't have it already. Just take a really closer look to this circuit before you're going to use KVL, KCL. Try to, if you can, somehow simplify your circuit or try to not define too many new variables. Okay, it's going to make you confused. So for this M2 we need VGS. The source voltage is already grounded, so we just need this gate voltage. What is the value for this gate voltage? This gate voltage, as you probably know, the gate of NMOS transistor are not gonna, you don't have the gate current. The gate current is 0. So you can assume that this R1 and R2 are in series. So if we define this node as Vx is equal to R2 divided by R1 plus R2 times Vout. And because these two are equal, so it's equal to Vout divided by 2. So I can use Vout divided by 2 for this node in here. By this definition, I can write what is the current through M2, because I already have GM. GM is 10 milliamp. And this is the gate source voltage for this node. Why gate source? Because source is already grounded. So this node defines our gate source voltage. So the drain current of M2 is equal to GM, which is 10 milliamp per volt, times VGS, which is Vout divided by 2. So it's equal to 5 Vout. But this drain current is in milliamp. Be careful. These units are really important. So 5 Vout for this current. And now how about M1? How about M1? Let me change the color for M1. Here this is the gate voltage grounded. How about this voltage? How we can define this voltage? For example, you can set that this voltage is equal to a new variable such as Y. Okay? Now I'm gonna extract a new formula for Vy relating to these parameters, because we're looking for Vout divided by I in. Okay, so it's better to, if you define new parameters, you somehow relate them to the Vout or I in. This is really important. So if this is Vy, so we define gate source voltage of M1 0 minus Vy, which is minus Vy. So this current is equal to GM1, which is 10 times VGS. VGS 0 minus Vy, which is minus Vy. This is the current through M1. And if you seen here, you can use KCL at this node, at Vout. This is one current, so minus 10 Vy, and the other current is this one, Vout divided by these two resistors, plus Vout divided by R1 plus R2, which is 200 kilo ohm, equals to 0. Now we can calculate Vy. It's completely obvious by simple mathematics. Vy equals to Vout divided by 2000. So this is the really small value. It's almost zero. It's almost zero. It's really negligible. But I'm gonna write the final formulas and you can judge it then. Okay? Now, the last thing we're gonna do is use KCL at this node, because we look for the relationship between Vout divided by I in. So KCL at Vy. This is the last thing that we need. So I in is coming in, so minus I in. This one, 5 Vout is coming out, plus 5 Vout. And this current, minus 10 Vy, minus 10 Vy is coming in actually. So minus 10y, which is plus 10y, 10 Vy, equals to 0. This is the KCL for this node. Okay. Now you can write it like this. Minus I in plus 5 Vout plus 10 Vy. 10 Vy is actually Vout divided by 200 equals to 0. Actually, you can write it just like that, because this current is equal to this current. You can simply forget about Vy and just say that this is the same current as this one, so it's already Vout divided by 200. Okay, now if we organize this somehow, 5 plus 1 divided by 200 times Vout equals to I in. So what is the value for Vout divided by I in? Equals to 1 divided by 5 plus 1 divided by 200. And as you can see, 1 divided by 200 is a really small value compared to 5. So it's equal to 1 divided by 5. But what is the unit for Y? As I already mentioned, that this is milliamp. So this is 1 divided by 5 milliamp, which is equal to 1000 divided by 5, which is 200 ohm. So the option here is C. But as I look at it right now, you can eliminate the definition of Vy, and from the beginning you can set that this is the current for this transistor. This is the current. This is the drain current of this transistor. Vout divided by 200 kilo ohm. So it's going to make it so much easier to calculate. It's going to eliminate this stage to make it much more simpler than it is. I hope you like this video. If that's the case, please give me a thumbs up and share this video with your friends. And again, if you have any questions relating to this video, please let me know in the comment sections. Thanks for watching.